Tonight, we're traveling far deeper than human history to a time nearly 50 million years ago when Earth existed in a state that now feels almost impossible. The planet carried its warmth evenly. There was no permanent ice at the poles. Heat moved freely through the oceans and the air, reaching even the highest latitudes. The far north was not a frozen boundary. It was a place where water remained liquid, where summers lingered, where life could persist without retreating from the cold. Forests stretched farther toward the poles. Seasons followed gentle rhythms, and for millions of years that balance held. And then, without announcement, that balance began to change. The planet started to cool, not abruptly, not violently, but steadily enough that the shift went unnoticed by life at the surface. Ice began to linger in places where it once vanished every year. Ocean circulation slowly reorganized. Carbon dioxide levels in the atmosphere began to fall, not in a sudden drop, but in a long, quiet decline that would reshape the future of the planet. Deep within Earth's geological record, a subtle signal began to appear. Atmospheric carbon dioxide was declining over a long stretch of time. Not a brief drop, but a sustained removal. Too much to be explained by ordinary processes. Too consistent to be dismissed as chance. For decades, scientists searched for the cause, and the trail led somewhere unexpected. Not to fire, not to rock, not to catastrophe, but to something alive, small enough to drift at the surface of the water. But how could something so simple influence the balance of an entire planet? And once that balance shifted, why did Earth never fully return to the world it had been before? Tonight, we'll move gently into that ancient world and follow the subtle chain of events that helped guide Earth toward a colder future. But before we begin, I'd love to know where you're listening from tonight and what time it is there. Reading your comments is one of my favorite parts of this calm little community. If you enjoy these slow journeys through deep time, a like and a subscribe help this channel reach others. Now take a slow breath in, let your shoulders relax, and together let's drift into the moment when something almost invisible changed the fate of our planet. Long before ice claimed a lasting place at the poles, Earth entered a period shaped by warmth that reached almost everywhere. This interval unfolded quietly, defined not by extremes, but by a steady distribution of heat that softened the contrast between equator and pole. The planet moved energy with ease, allowing climates to blend gradually rather than fracture into sharp zones. Global temperatures remained significantly higher than those of the modern world. The atmosphere held warmth efficiently, while the oceans absorbed and released heat at a measured pace. Seasonal differences existed, but they rarely pushed ecosystems toward collapse or dormancy. Instead, long stretches of stable conditions allowed environments to settle into predictable rhythms. At high latitudes, the absence of permanent ice changed everything. Snow could fall during darker months, yet it seldom lingered. As light returned, thin coverings of ice dissolved back into water. The poles did not function as frozen boundaries, but as active participants in the global circulation of air and ocean currents, sharing warmth rather than resisting it. Sea levels rose in response to this ice-free world. With little water stored on land, the oceans expanded outward, covering wide continental margins. Coastlines shifted slowly over time, reshaping shallow seas and creating broad, sunlit shelves. These regions stored heat efficiently, reinforcing the planet's overall temperature balance and buffering against sudden shifts. Warm conditions stretched far into regions now defined by cold. Forests extended deep into northern latitudes, supported by soils that never locked into ice. Wetlands persisted year-round. Rivers flowed without interruption. Growth followed long, uninterrupted cycles, and ecosystems developed layers of resilience rooted in consistency rather than adaptation to extremes. The atmosphere played a steady supporting role. Elevated levels of greenhouse gases reduced heat loss, maintaining a planet that cooled only gradually between seasons. This was not a world of uniform warmth, but one where moderation prevailed. Climatic boundaries remained flexible, allowing gradual transitions rather than abrupt thresholds. Patterns of wind and water circulated with little resistance. Ocean currents carried warmth poleward, while atmospheric systems redistributed energy across continents. The result was a planet that felt connected across vast distances, its systems linked in slow continuous exchange rather than divided into isolated regimes. This warmth did not announce fragility. From the surface, the world appeared settled, even generous. Life expanded into available space, and the physical environment offered few hints of instability. Yet beneath this calm persistence, subtle processes continued to operate, accumulating effects too gradual to register on human scales of observation. The Eocene unfolded as an era of balance and quiet endurance. High seas, ice-free poles, and extended warmth formed a stable backdrop against which deeper changes could gather unnoticed. Earth moved forward within this gentle equilibrium, carrying conditions that seemed permanent, even as the foundations of a different climate future slowly took shape. At the northernmost edge of the planet, the ocean did not yet behave like the one familiar today. Its boundaries were shaped differently, its connections incomplete, its movements restrained by geography that altered how water entered, lingered, and left. The Arctic basin existed as a space more contained than open, influenced as much by surrounding land as by the wider global ocean. Rather than flowing freely into neighboring seas, this ocean was only partially connected to the rest of the world's waters. Narrow passages limited exchange, slowing the movement of currents that elsewhere helped blend temperature, salinity, and chemistry. Water entered and exited, but never with enough force to fully mix the basin. Circulation remained muted, creating a system that responded sluggishly to outside influence. From the continents surrounding it, fresh water arrived in steady abundance. Vast rivers drained warm landscapes to the south, carrying meltwater, rainfall, and sediment northward. Over time, this input accumulated, pouring into the basin faster than it could be removed. The surface grew progressively fresher, lighter than the saltier water below, changing how the ocean layered itself from top to bottom. Because fresh water resists sinking, it spread outward across the surface, forming a broad, stable layer that floated above denser marine water. This stratification reduced vertical mixing, separating the upper ocean from the depths beneath. Nutrients, heat, and oxygen moved more slowly between layers, creating a calm surface environment distinct from the darker water below. The shape of the basin amplified these effects. Sheltered by surrounding land masses, winds had less influence on overturning surface waters. Without strong currents to disrupt it, the freshwater cap remained intact for long periods. Seasonal changes came and went, but the structure of the ocean endured, persistent enough to shape chemistry, temperature, and biology in quiet ways. Salinity gradients sharpened, the surface stayed fresh, while deeper waters retained their marine character. This separation altered how heat was stored and released, allowing warmth to remain near the surface instead of dispersing downward. Light penetrated easily through calm water, while the stability of the upper layer reduced turbulence that might otherwise disturb delicate processes unfolding there. The Arctic of this time was not harsh or forbidding. It was sheltered, layered, and unusually still for an ocean basin. Its waters responded slowly, held in place by geography, and sustained by constant freshwater input. Compared to other oceans that churned and circulated across the globe, This northern basin developed its own internal rhythm. These conditions did not announce themselves with visible markers. There were no sudden shifts in shoreline or dramatic changes in color from above. The transformation existed in gradients, in the quiet persistence of separation between surface and depth. Over long spans of time, this isolation allowed the Arctic Ocean to behave less like a mixing ground and more like a contained system shaped by restraint rather than motion. Within this enclosed, gently layered sea, the stage was set for processes unlike those elsewhere on Earth. Geography had created an environment where water lingered, layers remained distinct, and subtle imbalances could persist without immediate correction. The Arctic became not just a place on the map, but a unique oceanic space governed by stillness, accumulation, and time. At the very top of the world, a quiet sorting began to take hold, governed by a simple physical rule that shaped everything that followed. Water arriving from land carried less salt than the sea beneath it, and that difference mattered. Fresh water remained lighter, resistant to sinking, content to spread outward rather than descend. As time passed, this lighter water accumulated at the surface. Layer by layer, it formed a broad cap that floated above the denser ocean below. The boundary between them sharpened gradually, not as a visible line, but as a persistent separation felt through temperature, chemistry, and motion. The upper ocean became its own domain, connected to the depths only by slow exchange. This stratification changed how the Arctic surface behaved. Winds still passed over it, seasons still shifted light and darkness, but the water itself resisted disturbance. Vertical mixing weakened. Nutrients from below rose more slowly. Heat lingered near the surface, instead of dispersing into deeper layers. The ocean began to behave less like a rotating column and more like a stacked system, calm above, heavier below. With reduced mixing came stillness. The surface waters smoothed, their movements dampened by the buoyancy holding them in place. Chemical conditions diverged as well. Oxygen levels, nutrient availability, and dissolved gases followed patterns distinct from those deeper down. This separation did not produce immediate drama. Instead, it created consistency, a surface environment that changed gently rather than abruptly. The persistence of this freshwater layer mattered more than its thickness. It returned season after season, reinforced by continued input and limited removal. Even when surface conditions fluctuated, the layered structure endured. Each year added another quiet confirmation that the surface and the depths belonged to different regimes. Light interacted differently with this stabilized surface. With fewer disturbances, sunlight penetrated evenly, lingering within the upper layer rather than scattering unpredictably. Energy remained concentrated near the top, supporting processes that favored calm, exposure, and continuity. The Arctic surface became a place where subtle shifts could persist, long enough to matter. Chemical distinctions grew clearer over time. Elements entering the surface waters followed slower pathways out. Gases exchanged with the atmosphere differently than they did elsewhere. The ocean, usually defined by motion and mixing, here adopted patience. Processes unfolded on extended timescales, shaped less by turbulence and more by steady presence. This was not isolation in the sense of separation from the world, but a narrowing of interaction. The surface still responded to seasons and climate, yet it did so on its own terms. It absorbed change gradually, filtered through layers that softened extremes and preserved imbalance rather than correcting it quickly. The Arctic surface became calm, not through absence of forces, but through their gentle containment. Freshwater held its place, buoyed and persistent, maintaining a chemically distinct environment that resisted disruption. In that calm persistence, the ocean acquired a rare quality, a surface capable of sustaining conditions that elsewhere would dissolve back into motion. What emerged was a stable upper world, quiet and continuous, shaped by lightness and restraint. At the top of the planet, water learned to remain where it arrived, and in doing so, created a setting where slow accumulation could unfold without interruption, guided by gravity, chemistry, and time. Stability has a way of inviting growth. Where conditions change slowly and predictably, life finds room to expand, not in sudden bursts, but through steady presence. In the Arctic surface waters of this era, the environment offered exactly that kind of consistency, a setting where biological processes could unfold without frequent interruption. The water near the surface remained calm for long stretches of time. Nutrients delivered from rivers and recycled within the upper layers lingered instead of being rapidly dispersed. With limited mixing to carry them away, these materials stayed accessible, circulating gently within the same shallow zone. The surface became quietly enriched, not through dramatic input, but through retention. Above it all, light followed an unusual rhythm. During Arctic summers, the sun did not rise and set in the familiar pattern. Instead, daylight stretched on without pause, bathing the surface waters in continuous illumination. Hours blended together, then days, then weeks of unbroken light. Photosynthetic organisms experienced no true night, only gradual shifts in angle and intensity. This combination mattered. Nutrients remained available, light remained constant, temperatures stayed within a narrow range. Growth no longer had to pause and reset. It could continue, reinforcing itself through repetition rather than competition. Each cycle fed the next, allowing productivity to climb beyond levels seen in more turbulent waters. Plant life at the surface responded accordingly. Microscopic and floating organisms multiplied, spreading across the calm upper layer. Their presence thickened gradually, season after season, not as fleeting blooms, but as sustained coverage. The surface water became increasingly occupied by living material, reshaping how energy and matter moved through the system. As this biological presence expanded, it altered the environment in subtle ways. Light penetration changed as surface growth increased. The chemistry of the water shifted as organisms absorbed and released elements during growth and decay. These changes did not disrupt stability. They deepened it, creating conditions that favored continued dominance rather than balance. The system began to lean toward excess, though not in a chaotic sense. Productivity outpaced removal. Growth exceeded decay. Material accumulated faster than it could be redistributed or broken down. This imbalance remained gentle, guided by the same calm forces that allowed it to form. Nothing collapsed. Nothing was corrected quickly. What made this shift unusual was its persistence. In most oceans, turbulence, mixing, and seasonal change limit how far productivity can climb before resetting conditions. Here, those limiting forces were softened. The surface remained sheltered, well lit, and chemically distinct, long enough for accumulation to matter. Life did not surge forward in a single moment. It advanced quietly, layer by layer, generation by generation. Each addition was small, but together they altered the character of the surface ocean. The Arctic became a place where biological activity was not merely present, but sustained at a level rarely possible elsewhere. This transformation carried no visible boundary. There was no point at which abundance suddenly appeared. Instead, the environment drifted toward a state where growth was no longer checked by instability. In that steady calm, life expanded until productivity itself became a defining feature of the Arctic surface, shaping the system through presence rather than force. Azolla entered this environment without drawing attention to itself. It did not arrive as a towering forest or a drifting bloom that flashed and faded. It existed close to the surface, small and self-contained, floating quietly where fresh water rested above the sea. Individually, each plant was modest, easy to overlook within the broader movement of water and light. Yet Azolla possessed an unusual way of growing. When conditions allowed, its expansion accelerated rapidly, not upward, but outward. New fronds branched from old ones, spreading laterally across the surface. This growth favored coverage rather than height, allowing the plant to occupy space efficiently, linking individual forms into continuous mats that drifted as a single living layer. Because it floated, Azolla remained directly within the zone of strongest light. It did not depend on anchoring to the seafloor or competing for access to sunlit water. Wherever the surface remained calm, it could persist, riding the boundary between air and water where energy was most available. This positioning allowed growth to continue uninterrupted for long periods. Its most remarkable trait, however, lay hidden within its tissues. Azolla hosted microscopic partners capable of capturing nitrogen from the atmosphere. This relationship supplied the plant with a steady source of a nutrient that typically limits growth in aquatic environments. While other organisms slowed when nitrogen became scarce, Azolla carried its own supply. This internal source of nitrogen changed the rules that governed surface productivity. Growth no longer depended solely on what the water could provide. It drew directly from the air above, bypassing a constraint that normally prevents unchecked expansion. The plant became less tied to cycles of depletion and renewal that restrain most biological systems. As Azolla spread, its mats thickened. Fronds overlapped, creating layered coverage that shaded the water beneath. The surface became increasingly occupied, its character altered by the presence of living material that absorbed light, exchanged gases, and interacted constantly with the surrounding water. Movement slowed further as the mats dampened wind-driven disturbance. Despite this presence, the plant did not disrupt the calm that supported it. Its growth aligned with the existing stillness, reinforcing stability rather than breaking it. Each generation added to the surface without forcing rapid correction. Expansion occurred through repetition, not sudden bursts, allowing Azolla to remain dominant once established. What made Azolla especially unusual was this combination of traits. It floated, it spread horizontally, it grew rapidly, and it escaped one of the most common limits on biological expansion. Individually, none of these characteristics were extraordinary. Together, they allowed the plant to behave differently from most aquatic life. Over time, the Arctic surface supported a living layer that renewed itself continuously. Old growth aged and broke apart while new fronds filled the gaps. The system favored persistence rather than fluctuation. Azolla did not need exceptional events to thrive. It relied on consistency, light, and time. In this way, a small freshwater fern became something more than a minor presence. Without force or noise, it occupied the surface steadily, sustained by conditions that rarely disrupted its rhythm. Its unusual biology allowed it to take advantage of calm in a way few organisms could, turning stability itself into an engine of expansion. Growth changed its character quietly, without crossing any visible line. What had once expanded in step with its surroundings began to move ahead of them. The surface no longer reset itself between seasons. Coverage returned, thickened, and remained, turning repetition into permanence as the living layer learned to stay. Azolla spread outward across the water with increasing reach. Individual plants linked together until separation disappeared, forming continuous mats that drifted as unified sheets. Open water narrowed. What had been scattered presence became near total occupation, reshaping the surface into a living skin that followed the contours of stillness. As these mats widened, light changed below them. Sunlight that once passed freely into the upper water column now met resistance. Shadows formed where brightness had been even. The energy reaching deeper layers weakened, not abruptly, but steadily, as coverage became more complete and persistent. This shift altered competition without confrontation. Organisms beneath the mats did not vanish suddenly. They declined gradually, starved not by removal, but by exclusion. With less light and reduced exchange, their growth slowed until presence thinned and influence faded from the system. The surface, meanwhile, continued to favor what already dominated it. Azolla thrived where calm, light, and nutrients remained available. Its growth did not trigger correction. Instead, expansion strengthened the very conditions that allowed it, reinforcing stability at the surface while deepening separation below. What emerged was a feedback loop rooted in persistence rather than disruption. More coverage led to calmer water. Calmer water favored continued spread. Seasonal limits softened. Growth no longer peaked and retreated. It accumulated, carrying itself forward through time by maintaining the environment it preferred. This persistence marked a turning point. In many ecosystems, growth is constrained by cycles that restore balance through mixing, disturbance, or depletion. Here, those cycles lost strength. Expansion no longer waited for favorable moments. It simply continued, supported by conditions that rarely shifted enough to interrupt it. Material gathered at the surface as living mass replaced open water. Organic matter entered a slower rhythm of change, aging and renewing within the same confined zone. Production exceeded breakdown. The system leaned gently toward excess, not through acceleration, but through endurance. Nothing in this transformation appeared sudden from above. The water remained calm. The surface looked continuous rather than chaotic. Yet beneath that calm lay a clear imbalance. Growth had stopped responding to limits and begun to set them instead. This was not collapse, nor competition driven by force. It was a quiet reordering, where one form of life gradually occupied the rules of the environment itself. Expansion became the default state, no longer seasonal, no longer self-correcting. In that sustained dominance, the surface crossed into a new condition, one defined not by growth alone, but by growth that no longer returned the space it claimed. The surface did not return to openness once growth took hold. Instead, coverage endured, spreading far beyond local patches and seasonal moments. Evidence preserved in sediment and chemistry points to a bloom that reached across vast portions of the Arctic basin, extending over areas large enough to reshape surface processes on a regional scale. This was not a single episode frozen in time. The bloom returned again and again, unfolding across long spans that exceeded ordinary ecological cycles. Each phase followed the same quiet pattern: expansion across calm water, persistence through favorable seasons, then renewal rather than disappearance. What faded in one interval was replaced in the next, maintaining continuity rather than allowing reset. Some periods of dominance stretched far beyond any human sense of duration. The surface remained occupied for thousands of years at a time, long enough for short-term fluctuations to lose importance. Within these spans, the Arctic surface behaved less like an ocean in motion and more like a sustained biological platform, its character shaped by what remained rather than what passed through. The scale of this persistence mattered. A bloom confined to narrow regions would have left only local traces. Instead, Azolla's reach appears to have extended across much of the basin, forming a connected presence that linked distant surface waters into a shared system. Material produced in one area influenced conditions elsewhere, bound together by slow drift and prolonged residence at the surface. With this scale came endurance. The bloom did not depend on rare alignments or exceptional years. It relied on conditions that, once established, remained stable enough to support repetition. Growth returned not because circumstances reset, but because they never fully reversed. The surface retained the features that allowed dominance to resume. As centuries passed, then millennia, the Arctic surface developed memory. Each cycle left behind traces that shaped the next. Organic matter accumulated, chemical signals built upon one another. Even when coverage thinned briefly, the system remained predisposed toward renewed expansion. Persistence became structural rather than episodic. This long duration altered how time functioned within the system. Short-term disturbances lost their ability to redirect outcomes. The bloom absorbed variation and continued. What would elsewhere serve as a limiting interruption became a minor ripple within an ongoing pattern of dominance. The Arctic surface therefore existed in a sustained state, unlike most oceanic environments. It did not alternate cleanly between abundance and scarcity. It remained continuously influenced by the presence of a living layer that shaped light, chemistry, and exchange over enormous spans of time. The bloom was not an event to be marked and passed. It was a condition that held. Through repetition and persistence, Azolla's presence transformed scale into influence. The longer it remained, the more thoroughly it defined the surface. Thousands of years blurred together into a continuous biological era, one that left clear signatures behind, despite its quiet nature. In this sustained dominance, the Arctic surface crossed from temporary imbalance into prolonged redefinition. Growth was no longer an episode within the system. It became the system itself, enduring long enough to matter not just locally, but planet-wide. Death did not end the story at the surface. When growth reached its limits and older fronds aged beyond renewal, Azolla followed gravity downward, slipping quietly from light into depth. The living layer thinned as fragments detached, drifting through the water column toward a seafloor that waited far below. This descent happened steadily rather than all at once. Pieces of plant matter fell in pulses shaped by time and accumulation, not by sudden collapse. The journey carried organic material out of the surface system and into darker layers where conditions were very different from those above. Near the bottom, oxygen was scarce. The same layering that supported surface persistence also restricted exchange with deeper waters. Without regular mixing, fresh oxygen arrived slowly. This shortage mattered. In well-oxygenated environments, plant material breaks down rapidly, returned to circulation through decay. Here, that process slowed. As Azolla settled onto the seafloor, decomposition lost its urgency. Microbial activity continued, but at a reduced pace. Material accumulated faster than it could be processed. Leaves and fragments layered atop one another, pressed gently into soft sediment, their chemical signatures preserved rather than erased. Burial followed naturally. Each new delivery of organic matter added weight, sealing older material beneath it. Fine sediments carried by water settled over the remains, isolating them further from oxygen and disturbance. What might elsewhere have returned to the atmosphere instead slipped into long-term storage. This transition marked a quiet shift in the carbon cycle. Carbon absorbed from the air during growth was no longer passing back upward through decay. It moved downward, locked into sediment where exchange with the atmosphere slowed to geological time. Removal did not occur through violence or disruption, but through patience. The scale of this burial mattered as much as the process itself. Repeated delivery over thousands of years built thick layers enriched with organic carbon. Each cycle reinforced the last, increasing the volume stored below, while surface systems continued to supply more. The imbalance between uptake and release grew slowly, almost invisibly. Nothing about this burial announced itself on the surface. The water remained calm, growth continued above. Yet below, the seafloor quietly changed character, becoming a record of accumulation rather than recycling. Carbon that once moved freely between ocean and air now rested beyond reach. This was not permanent in the sense of eternity, but it was durable. Once buried, the carbon remained isolated long enough to alter the balance of the larger system. Short-term fluctuations lost relevance. What mattered was duration, the steady continuation of burial without equal return. The seafloor thus became an archive written layer by layer. Each deposit captured a moment of growth transformed into storage. Over time, these layers told a consistent story of excess production paired with slowed breakdown, a combination rare enough to matter on a planetary scale. In this way, the death of surface life became an agent of long-term change. What sank did not vanish. It settled, accumulated, and stayed. Carbon shifted from circulation into memory, pressed into sediment where its influence would extend far beyond the life of the plant that carried it there. Carbon dioxide does its work quietly, unseen yet constant, shaping how much warmth Earth retains from the sun. It allows incoming energy to linger, slowing its escape back into space. When this gas remains abundant, heat is held within the atmosphere and oceans, smoothing cold and supporting warmer global conditions. When carbon dioxide is reduced, the effect unfolds slowly. Less heat is retained with each passing year. Nights cool a little more. Seasonal warmth fades slightly earlier. No single moment announces the shift. Instead, temperature responds through accumulation, adjusting step by step as balance changes. What matters most is time. Short-term fluctuations leave little mark on the climate system, but sustained removal alters its baseline. Over thousands of years, even small reductions compound. The planet gradually settles into cooler averages, and systems shaped by warmth begin to reorganize. During the long dominance of surface growth in the Arctic, carbon followed an unusual path. Through photosynthesis, Azolla drew carbon dioxide from the atmosphere and stored it as living tissue. As long as growth continued, this removal operated steadily, season after season, without interruption. Because the plant's remains were buried rather than rapidly broken down, much of that carbon did not return to circulation. The usual exchange between air, water, and life slowed. Carbon moved downward into sediment, leaving the atmosphere incrementally leaner with each passing cycle. This removal did not need to be dramatic to matter. It did not rely on sudden drops or rare events. It functioned through persistence. Year after year, carbon was taken in at the surface and stored below, shifting the balance almost invisibly. The atmosphere responded not with shock, but with gradual adjustment. As carbon dioxide levels declined, Earth's ability to hold heat weakened. Oceans began to release warmth more readily. Seasonal cooling lingered longer at higher latitudes. Temperature differences sharpened gently, allowing cooler conditions to gain a foothold where none had lasted before. The climate system absorbed these changes slowly. Air and water responded over long intervals, adjusting circulation patterns and energy flow. Feedbacks emerged quietly. Cooler conditions encouraged processes that supported further cooling, not through force, but through reinforcement. Azolla's role in this shift was indirect yet sustained. The plant did not influence temperature by altering sunlight or circulation on its own. Its impact came from carbon removal repeated over immense spans of time. Each generation contributed a small subtraction. Together, they created a meaningful change. What makes this process remarkable is its patience. The cooling that followed did not announce a turning point. Life continued, growth persisted. Yet beneath that continuity, the planet was losing a portion of its stored warmth. The adjustment remained gentle enough to avoid disruption, yet persistent enough to matter. Carbon dioxide did not vanish. It relocated, moving from air to living matter, then into sediment. In doing so, it altered the long-term energy balance of the planet. Temperature followed carbon's lead, responding slowly but faithfully to its absence. Through this continuous removal, Earth's climate began to drift away from the warmth it once maintained so easily. The change required no catastrophe. It emerged from repetition, storage, and time, proving that even gradual shifts in carbon can reshape a world. Long after the surface changed and growth faded from view, the Arctic retained a record of what had occurred, pressed quietly into its depths. Beneath layers of water and time, the seafloor accumulated evidence not through spectacle, but through patience, receiving material that settled and stayed. Sediment built slowly on the Arctic floor, grain by grain, layer by layer. Within these deposits, certain intervals stand apart. They appear darker, richer, heavier with organic material than the sediments above and below them. These layers do not announce themselves dramatically. They reveal their significance only when examined carefully, as subtle deviations from an otherwise steady background. When scientists retrieved cores from the Arctic seafloor, these organic rich layers emerged as a recurring feature. Their thickness suggested prolonged accumulation rather than brief events. Material had arrived continuously, not in pulses tied to singular disturbances. The sediments told a story of persistence, written in compressed time. The age of these layers aligned with the period when surface conditions favored extensive plant dominance. Independent dating methods placed their formation within the same broad interval suggested by surface reconstructions. The timing was consistent across multiple cores, even when collected from distant parts of the basin. This agreement reduced the likelihood of coincidence. Chemical analysis deepened the picture. Carbon preserved within these layers carried isotopic patterns associated with plant matter rather than marine algae or inorganic sources. The ratios reflected carbon that had passed through photosynthesis before burial. This signature linked the sediments directly to biological production at the surface. These isotopic fingerprints mattered because they separated cause from background noise. Oceans accumulate organic material continuously, but not all carbon leaves the same trace. The patterns within these layers pointed to a specific pathway, carbon drawn from the atmosphere, incorporated into plant tissue, then transferred downward without rapid recycling. The physical structure of the sediments reinforced this interpretation. Fine layering indicated low disturbance at the seafloor. Currents did not remix the deposits aggressively. Once material arrived, it remained largely where it settled. This stability preserved detail that would otherwise have been erased. Across multiple sites, the same features appeared: organic richness repeated, isotopic signals aligned, thickness remained substantial. The consistency suggested a basin wide process rather than isolated pockets of unusual deposition. The Arctic seafloor behaved as a collective archive, recording a shared history. Nothing within these cores suggested sudden catastrophe. There were no abrupt breaks, no sharp transitions signaling collapse or destruction. Instead, the record showed continuity, a long interval where accumulation outpaced removal. The quiet nature of the sediments mirrored the quiet nature of the surface processes that produced them. This buried record matters because it does not rely on inference alone. It exists as physical material that can be measured, compared, and dated. The story of surface dominance and carbon burial is not reconstructed only from models or indirect clues. It is present in the rock itself. Through these sediment layers, the Arctic preserved memory. Growth that once floated in sunlight left its mark in darkness, pressed into the seafloor, where time moved slowly. Long after the bloom ended, its signature remained, confirming that what unfolded above was real, sustained, and large enough to become part of Earth's geological record. Change unfolded on a timescale that resisted urgency. The processes shaping Earth's cooling did not compress themselves into brief intervals. They stretched outward across hundreds of thousands of years, long enough that no single generation of life would have perceived a beginning or an end. Carbon removal operated steadily rather than forcefully. Each year, a small amount left circulation. Each century, that subtraction added up. Over immense spans, these increments accumulated into a measurable shift. The atmosphere did not react with sudden imbalance. It adjusted slowly, releasing heat a little more efficiently as carbon dioxide declined step by step. Because the change was gradual, the planet never experienced the shock associated with rapid climate disruption. There were no sharp boundaries separating one state from another. Temperature trends moved gently, often masked by ordinary variability. Warm years still followed cooler ones. Seasonal rhythms continued. Yet beneath those familiar cycles, the baseline was drifting. Ecosystems responded in kind. Life is sensitive to rate as much as magnitude, and here the pace allowed adjustment. Species ranges shifted without collapse. Communities reorganized over long periods, tracking conditions as they moved, rather than confronting abrupt thresholds. Forests retreated or advanced incrementally. Oceans altered circulation patterns without breaking them. This long duration also softened feedbacks. Processes that might accelerate cooling under rapid change remained restrained. Ice did not surge suddenly. Reflectivity increased only after colder conditions had already persisted. Each response waited for the last to settle, creating a sequence of gentle reinforcement instead of runaway reaction. The slow pace mattered for chemistry as well. Ocean and atmosphere exchanged gases continuously, smoothing out short-term fluctuations. Carbon removal at the surface fed into long-term storage below without forcing immediate atmospheric imbalance. The system absorbed change through redistribution rather than rupture. Cooling therefore accumulated quietly. There was no single moment when the planet crossed into a colder world. Instead, it drifted, carrying traces of its warmer state even as it slowly released them. Heat lingered, then lingered a little less, until persistence gave way to memory. This gradual shift allowed Earth to remain functional throughout the transition. Circulation continued, life remained abundant. The planet did not pause or reset. It adjusted while moving forward, integrating change into its ongoing patterns rather than isolating it as an event. Time itself became an active component. Lengthened intervals turned small differences into meaningful outcomes. What would have been negligible over centuries became transformative over hundreds of thousands of years. Cooling did not need intensity, it relied on duration. In this way, patience shaped the outcome. Carbon left the atmosphere slowly enough to avoid disruption, yet consistently enough to matter. Temperature followed, responding faithfully to the long trend rather than short swings. The planet's systems remained flexible, able to adapt without breaking. By the time cooling became unmistakable in the geological record, it had already been underway for ages. The change felt smooth because it had been layered into existence. Earth arrived at a new state not by crossing a threshold, but by walking a long, unhurried path shaped by accumulation, adjustment, and time. Ice did not arrive as a sudden curtain closing over the poles. It appeared quietly, first as a seasonal feature that came and went with the light. During colder months, thin sheets formed at high latitudes, fragile and temporary, part of a familiar rhythm rather than a lasting change. For a long time, these early formations disappeared each summer. As sunlight returned and temperatures rose, ice melted back into water, leaving little trace behind. The cycle repeated predictably, reinforcing the idea that cold could touch these regions but not remain. Gradually, that balance shifted. Summers still came, and melting still followed, but not completely. Small remnants endured beyond their usual limits, lingering into warmer months where they had once vanished entirely. These survivors were modest in size, easily overlooked, yet their presence altered what followed. Once ice remained from one season to the next, the system changed its behavior. Surviving ice reflected sunlight that open water would have absorbed, allowing surrounding areas to cool slightly more. That cooling favored further ice formation during the next winter, giving new growth a stronger foundation than before. Year after year, this process repeated. Each cycle built gently on the last. Ice did not surge outward dramatically. It accumulated, expanding its reach incrementally as persistence replaced disappearance. Coverage increased not through force, but through reliability. As ice remained longer, it began to influence its surroundings more consistently. Surface waters cooled earlier and warmed later. Seasonal contrasts sharpened. The presence of ice introduced a new element into circulation patterns, altering how heat moved through the system without disrupting it abruptly. Life adjusted alongside this change. Organisms accustomed to open water adapted to longer periods of cold. New boundaries formed gradually, allowing ecosystems to reorganize rather than collapse. The environment retained continuity, even as its baseline shifted. What mattered most was not the size of the ice at first, but its endurance. Persistence marked a transition from fluctuation to state. Ice was no longer just a response to winter. It became a feature capable of carrying its influence forward through time. As persistence strengthened, expansion followed naturally. Areas that once resisted long-term ice began to support it. Each surviving patch increased the likelihood of others enduring nearby. The system moved gently toward a new balance, guided by feedbacks that favored continuity rather than reversal. This moment did not announce itself loudly in the geological record. There was no single line where ice definitively arrived. Instead, evidence accumulated through patterns of survival and growth. What had once been seasonal became dependable enough to shape long term conditions. The persistence of ice marked a fundamental shift in Earth's climate behavior. It signaled that the planet had crossed into a regime where cold could sustain itself. The warmth that once erased every trace of winter no longer held absolute control. From this point forward, ice belonged to the system not as a visitor, but as a resident. Its continued presence did not end change, but it redirected it. The poles entered a new chapter defined not by the arrival of cold, but by its ability to stay, year after year, quietly reshaping the world around it. Once ice remained through the seasons, it began to alter the climate by its mere presence. Its surface interacted with sunlight differently than water or land ever had. Where dark ocean absorbed energy and stored warmth, ice reflected much of that light back into space. This redirection did not create cold on its own, but it reduced the amount of heat the planet retained, making cooling easier to sustain. As reflective surfaces expanded, even modestly, their influence accumulated. Each surviving patch contributed to a subtle shift in Earth's energy balance. Less solar energy entered the system, more escaped. The difference was small at first, but persistence turned it into a lasting change. Cooling oceans responded in parallel. As temperatures declined, seawater gained an increased capacity to absorb carbon dioxide from the atmosphere. This exchange occurred gradually, guided by chemistry rather than force. Cooler surface waters drew in more carbon, reducing its presence in the air and reinforcing the trend already underway. This transfer mattered because it linked temperature and carbon more tightly. Lower temperatures favored carbon uptake, and reduced atmospheric carbon favored further cooling. Neither process acted alone. Together, they formed a cooperative pattern where change in one supported change in the other without sudden escalation. Ocean circulation adjusted as well. Differences in temperature and salinity reshaped how water moved between regions and depths. Currents shifted their strength and pathways, altering how heat and dissolved gases were distributed across the planet. These changes unfolded slowly, carried by the same patience that defined the broader transition. With altered circulation came new patterns of exchange between surface and deep waters. Some regions became more efficient at storing carbon and heat below, while others released energy more readily. The ocean ceased to behave as it once had under warmer conditions. Its role in regulating climate evolved alongside the growing presence of ice. Feedback loops emerged not as runaway mechanisms, but as stabilizers. Ice encouraged cooling, cooling supported carbon removal, and reduced carbon favored the persistence of ice. Each element reinforced the others gently, creating a system that resisted return to earlier warmth without requiring dramatic forcing. These feedbacks did not accelerate endlessly. They settled into balance, defining a new baseline rather than driving collapse. The climate reached a colder state that could maintain itself through routine operation rather than extraordinary events. Stability replaced fluctuation as the defining feature. Importantly, this transformation respected continuity. Earth did not fracture into a new mode overnight. Life persisted, circulation continued, seasons still turned. Yet the rules governing the system had shifted. Ice was no longer a temporary outcome of winter. It became an active participant in climate regulation. By reflecting light, Absorbing carbon indirectly through cooler oceans and reshaping circulation, ice altered how Earth responded to energy. The planet gained a new capacity to hold on to cold. Warmth no longer erased itself each year. It had to compete with processes that favored restraint. Through these intertwined changes, the climate entered a state that supported its own persistence. The rules had changed quietly, without announcement. Ice no longer followed the climate alone. It helped govern it, guiding Earth into a colder balance that would endure far beyond the conditions that first allowed it to appear. Change did not remove dominance suddenly. It arrived through gradual shifts that altered the Arctic surface until the conditions that once supported persistence no longer held. The system did not break, it reopened. Salinity at the surface began to rise. Freshwater still arrived, but its influence weakened as circulation slowly strengthened. Connections between the Arctic and surrounding oceans became more effective, allowing saltier water to mix upward and fresh water to disperse outward. The layered structure that had once resisted disturbance softened. With increased salinity came density. Surface waters grew heavier, more willing to sink, less able to remain isolated above the depths. Vertical exchange increased, carrying heat, nutrients, and dissolved gases between layers that had long remained separate. The surface lost its chemical distinctness, and with it, its unusual stability. Ocean circulation reasserted itself gently. Currents that had once been muted gained strength and reach, restoring pathways that distributed energy and material more evenly across the basin. Water no longer lingered as long at the surface. Residence times shortened. Calm gave way to motion. These changes did not arrive as a reversal, but as a loosening. The Arctic surface remained productive, yet it no longer favored unchecked accumulation. Growth encountered renewed limits as nutrients were redistributed and light conditions fluctuated more widely. The environment became less predictable, less inclined toward persistence. For Azolla, this shift mattered profoundly. Its success depended on calm, isolation, and consistency. As mixing increased, those advantages faded. Mats thinned. Coverage broke apart. Expansion slowed until growth once again followed seasons rather than overriding them. The plant did not disappear immediately. It continued to exist within the Arctic, drifting, growing, and dying as it always had, but it no longer dominated the surface. It became one component among many, subject to the same constraints that governed other organisms in a more dynamic system. Surface isolation weakened further as circulation continued to adjust. Exchange with deeper waters increased oxygen availability at depth, accelerating decomposition of organic matter. Burial slowed. Carbon once again moved more freely between compartments. The long imbalance between production and recycling eased. Yet, by the time this transition unfolded, the climate had already shifted. The prolonged period of carbon removal had altered Earth's energy balance. Ice had learned to persist. Feedbacks favoring cooler conditions were established. The reopening of circulation did not undo what had accumulated. This asymmetry defined the end of dominance. Conditions that allowed Azolla to flourish were reversible. The consequences of its long success were not. Cooling persisted, even as surface biology returned to equilibrium. The system moved forward, carrying the imprint of what had come before. The Arctic emerged from this phase altered. Its surface once again mixed, circulated, and responded to variability. Yet beneath that return to motion lay a changed baseline. Carbon stocks differed. Ice dynamics differed. Climate behavior differed. Azolla's dominance ended without drama, fading as conditions shifted away from support. It left behind no monument at the surface. Its legacy rested elsewhere, in buried carbon, adjusted circulation, and a climate that no longer behaved as it once had. The plant stepped back into balance. The planet did not. After the long adjustment finished unfolding, Earth did not drift back toward its earlier warmth. The shift held. What had begun quietly at high latitudes expressed itself more clearly across the planet, settling into a condition that would define millions of years to come. In the southern hemisphere, ice sheets expanded across Antarctica. Snow that once melted between seasons now endured, compacting year after year into thickening layers. The continent became a stable reservoir of frozen water, anchoring cold in a way unseen during the planet's earlier warm phases. Ice no longer appeared as a temporary visitor. It took residence. This expansion reshaped global conditions without abrupt disruption. Sea levels adjusted gradually as more water remained locked on land. Atmospheric circulation adapted to new temperature contrasts between pole and equator. Oceans continued to move heat around the globe, but under altered constraints that favored cooler baselines rather than uniform warmth. Global temperatures stabilized at levels lower than those of the greenhouse world that preceded them. The planet did not plunge into permanent deep cold. Instead, it settled into moderation, shaped by restraint. Warm intervals still occurred, but they rose from a cooler starting point. Heat no longer spread as freely or persistently as it once had. This new balance reflected the combined influence of ice, carbon storage, and circulation. Feedbacks that once favored warmth had been weakened. In their place stood reinforcing processes that supported cold persistence without forcing extremes. The climate learned to hold onto cool conditions gently, integrating them into its long-term behavior. The earlier greenhouse world did not return because the system had changed internally. Energy moved differently. Carbon cycled differently. Ice influenced reflectivity and circulation in ways that prevented a full reversal. Even when external conditions shifted toward warmth, the planet resisted complete restoration of its former state. Life adapted within this settled framework. Ecosystems reorganized around new temperature ranges and seasonal patterns. The planet remained dynamic, but its range of motion narrowed, extremes softened. Stability became the defining feature of the post-turning point Earth. Time reinforced this condition. The longer the new balance held, the more firmly it rooted itself into geological and biological systems. Ice sheets shaped erosion and sedimentation. Cooler oceans altered nutrient distribution. The atmosphere adjusted its composition and flow in response to sustained conditions rather than fleeting trends. What emerged was not a frozen world, but one tempered by memory. Earth carried the imprint of its earlier warmth, yet no longer behaved as though that state were easily reachable. The path back required more energy than the system was willing to absorb. This persistence defined the turning point's outcome. The climate did not oscillate freely between past and present states. It moved forward into a configuration that favored endurance over reversal. Cooling had accumulated patiently, and its results proved durable. From this point on, Earth functioned within a new long-term balance. Ice anchored the poles. Carbon resided differently within the system. Temperature responded more cautiously to change. The greenhouse world receded into deep time, not erased, but left behind as the planet continued its story along a quieter, cooler course, shaped by accumulation, adjustment, and lasting transformation. Life did not vanish when conditions changed. It continued, adjusting its shape and reach as the planet settled into cooler patterns. The transition unfolded slowly enough that organisms were rarely forced beyond their limits. Instead of collapse, there was movement. As temperatures declined over long spans, species shifted their ranges. Populations followed suitable conditions as they migrated toward new latitudes or elevations. What once thrived closer to the poles gradually retreated, while other forms expanded into spaces newly opened by cooling. These changes did not arrive as waves of loss, they unfolded as reorganization. Ecosystems responded with flexibility. Communities adjusted their balance as relative advantages changed. Some relationships weakened, others strengthened. Food webs reshaped themselves incrementally, guided by availability rather than disruption. The pace allowed continuity even as composition changed. This gradualism mattered. Extinction events are defined by speed, by abrupt environmental shifts that outpace the ability of life to respond. Here, time acted as a buffer. Generations passed before conditions altered significantly. Adaptation became possible through adjustment rather than selection under crisis. New environments emerged alongside this shift. Expanding ice created novel habitats at high latitudes. Cooler oceans supported different circulation patterns that redistributed nutrients and energy. Terrestrial regions experienced altered rainfall and seasonality, giving rise to ecosystems unfamiliar but not uninhabitable. These emerging environments invited opportunity. Life filled them as it always had, exploring new configurations as old ones softened. Evolution proceeded not under pressure of survival alone, but through gradual fitting to a changing world. Diversity did not disappear, it rearranged. The fossil record reflects this continuity. There is no sharp boundary marking widespread loss. Instead, it shows overlap. Species coexist across the transition. Lineages persist while adjusting their roles. Turnover occurs without devastation. Earth itself facilitated this outcome. Its systems reorganized rather than fractured. Circulation shifted without stopping. Climate feedbacks stabilized new conditions instead of driving extremes. The planet absorbed change internally, redistributing stress across time and space rather than concentrating it into catastrophe. This capacity for reorganization is one of Earth's defining traits. When change arrives slowly, the planet responds by reshaping interactions rather than erasing participants. Balance is restored not through removal, but through adjustment. The absence of mass extinction does not imply insignificance. The changes were profound. Climate settled into a cooler regime. Ice became a permanent feature. Carbon cycled differently. Yet life remained continuous, threaded through the transition rather than severed by it. What emerged was a world transformed without being emptied. Lineages carried their history forward, altered but intact. Ecosystems bore the imprint of earlier warmth while adapting to cooler norms. The planet rewrote its rules without tearing out the pages. In this way, the Azolla-driven cooling stands apart from Earth's more violent transitions. It demonstrates how gradual change reshapes rather than destroys. Life endured because it was given time. Earth did not break under pressure. It reorganized, quietly, allowing continuity to persist even as the world became something new. For much of scientific history, the Arctic concealed its past simply by being where it was. The region resisted observation, not through secrecy, but through distance, cold, and physical barriers that limited access for centuries. Knowledge moved where tools could reach, and the far north lay beyond that boundary. The Arctic seafloor was among the most inaccessible places on Earth. Thick ice covered its surface for much of the year, drifting, fracturing, and reforming in patterns that defied stable navigation. Beneath that ice lay deep water, and below the water, sediment that recorded ancient conditions but offered no clues from above. Unlike exposed rock on land, nothing hinted at what waited underneath. Early understanding of Earth's climate relied heavily on regions that could be sampled directly. Mountains, deserts, coastlines, and shallow seas revealed their histories openly. The Arctic did not. Its record was submerged, insulated from erosion, and hidden beneath layers of ice that made long term study impractical. Absence of evidence was mistaken for absence of events. Even when climate models began suggesting unusual conditions in the ancient Arctic, physical confirmation remained elusive. The idea that a small plant could influence global climate seemed speculative without material proof. Without sediment cores from the region itself, the story could not be tested directly. It remained incomplete, scattered across indirect clues. The difficulty was not lack of insight, but lack of reach. Collecting samples from the Arctic seafloor required ships capable of operating in ice, drilling systems precise enough to penetrate deep sediment, and logistical support that could sustain long missions in extreme conditions. These capabilities emerged slowly, shaped by technological progress rather than sudden discovery. Only with modern drilling programs did the record begin to surface. Cores retrieved from beneath the Arctic Ocean carried layered sediments preserved with unusual clarity. What had been inaccessible for millions of years emerged as physical evidence that could be measured, dated, and compared. The story shifted from possibility to record. Reconstruction did not happen all at once. Each core answered some questions while raising others. Patterns had to be aligned across distances, dates refined, chemical signatures compared. Understanding grew incrementally, guided by patience rather than revelation. The narrative assembled itself, piece by piece. This slow unveiling mirrored the event itself. Just as the climate shift unfolded gradually, its discovery required time. There was no single paper or moment that revealed the full picture. The understanding emerged through accumulation, as separate findings aligned into coherence. The delay was therefore structural, not intellectual. Science advances where observation allows. When tools finally reached the Arctic depths, the past revealed itself without resistance. The evidence had waited, undisturbed, for conditions that allowed it to be seen. What scientists found was not dramatic in isolation. Organic rich layers, consistent timing, chemical signatures. Each feature spoke quietly. Together, they told a story that could not have been assembled earlier simply because the pieces were unreachable. This long delay in recognition highlights a broader truth about Earth's history. Some of its most influential changes leave subtle records, hidden in places that resist easy access. Discovery depends not only on curiosity, but on the ability to listen where the planet speaks softly. By the time the Arctic yielded its sediments, the event they recorded was long finished. Yet the story remained intact, preserved beneath ice and water, waiting for tools capable of hearing it. Science did not miss the event because it was invisible. It missed it because it was patient, buried, and far from reach, revealed only when time and technology finally aligned. This event stands apart because its engine was alive. Change did not begin with shifting plates, erupting volcanoes, or falling rock from space. It emerged from biology operating within favorable conditions, using ordinary life processes to produce an extraordinary outcome. The force that altered the planet did not fracture the ground beneath it. It floated at the surface, growing, dying, and repeating. Biological systems usually respond to climate. Here, biology helped shape it. The mechanism was not power, but persistence. Through continuous growth and long-term burial, living material altered atmospheric composition over immense spans of time. The planet did not react to a blow. It responded to pressure applied slowly enough to become part of its normal functioning. This pace is what separates the event from more familiar turning points in Earth's history. Many climatic shifts arrive violently, marked by abrupt boundaries in rock and fossil records. This one left no sharp line. It unfolded gradually, giving systems time to adjust rather than forcing them to break. Cooling accumulated quietly, guided by repetition rather than shock. Equally rare were the geographic circumstances that allowed biology to exert such influence. A partially enclosed Arctic basin limited circulation. Vast freshwater input supported stratification. Calm surface conditions persisted. Continuous summer light fueled productivity. These features aligned in a way seldom repeated elsewhere on Earth. Remove any one of them, and the outcome would have changed. Geography did not cause the shift on its own. It shaped the stage. Biology acted upon that stage through growth unconstrained by usual limits. The result was not inevitable, but contingent. This combination of location, water structure, and living processes formed a narrow window in Earth's history. The interaction between slow pace and rare setting is what made the event durable. Because change unfolded gradually, feedback stabilized instead of accelerating, ice learned to persist. Carbon cycles adjusted without sudden disruption. The climate moved into a new regime that could maintain itself long after the biological driver receded. Few events combine these traits. Biology rarely operates on scales large enough to influence global climate. Geography rarely aligns so precisely. And when climate does change, it often does so through rapid forcing that leaves unmistakable scars. Here, the record is subtle, preserved in sediments rather than catastrophe. The outcome was profound despite its quiet nature. Earth crossed from a warm world into one capable of sustaining long-term ice. That transition reshaped oceans, atmosphere, and life's distribution without erasing continuity. Change did not announce itself. It accumulated until its presence became undeniable. This uniqueness challenges how climate history is often understood. It shows that influence does not require intensity. Given time, even modest processes can redirect planetary behavior. The Azolla Event demonstrates how living systems, placed within the right conditions, can act as agents of lasting transformation. What makes this event distinct is not just what happened, but how. It was biological, gradual, and geographically specific. Few moments in Earth's past share that combination. Fewer still reveal how quietly a planet can change when life, time, and place align. Earth was never commanded by this process. Nothing issued instructions, and nothing dictated outcomes with precision. The planet moved according to its own internal rules, shaped by physics, chemistry, and circulation that long predated the event itself. Azolla did not steer those systems, it leaned on them. The climate of the time already existed near a point of balance. Warmth persisted, yet small changes could tip how energy moved and was stored. Carbon cycled steadily. Ice appeared and vanished seasonally. The system was stable, but not rigid. It could respond to pressure if that pressure arrived patiently enough. Azolla applied that pressure without intent. Through growth and burial, it altered carbon flow incrementally, placing weight on one side of the balance rather than overturning it. Each cycle nudged conditions slightly away from the earlier state. No single step forced change. The accumulation did. Climate responds not to moments, but to totals. A brief disturbance is often absorbed and forgotten. Sustained influence behaves differently. When small effects repeat without interruption, the system adjusts around them. Azolla's influence worked in this way, adding the same quiet signal again and again until it mattered. The planet retained agency throughout the process. Feedbacks emerged because Earth's systems respond to imbalance by redistributing energy and material. Ice expanded because colder conditions favored persistence. Oceans absorbed more carbon because chemistry allowed it. Circulation shifted because gradients changed. None of these responses were directed by biology. They followed their own logic once conditions changed. This distinction matters. Control implies intention and dominance. Influence implies participation. Azolla participated in Earth's systems by feeding into pathways that already existed. It did not invent feedbacks or override circulation. It supplied input that those mechanisms processed over time. Small forces often appear insignificant when viewed in isolation. A single growing season, a single layer of sediment, a minor shift in carbon concentration. Yet, when these forces repeat across thousands of years, they accumulate into direction. Climate responds faithfully to that direction, regardless of how quietly it was set. The long timescale transformed modest influence into lasting change. What mattered was not the strength of any individual contribution, but the absence of interruption. Growth continued, burial continued, removal continued. Earth responded because the signal never faded. This pattern is common in planetary history. Gradual processes shape landscapes, chemistry, and climate more often than sudden events do. Rivers carve canyons through repetition. Sediments build continents grain by grain. Climate shifts through sustained imbalance rather than single causes. Azolla's role fits this pattern precisely. It acted as one element among many, exerting influence without authority. The planet absorbed that influence and adjusted its behavior accordingly, guided by rules already in place. The outcome illustrates a broader principle. Control is not required for change. Consistency can be enough. When a small force persists long enough, it becomes part of the system's background, quietly shaping how responses unfold. In the end, Earth changed because it responded, not because it was directed. Azolla influenced conditions that were ready to move, and over long stretches of time, that influence was sufficient. Climate followed cumulative pressure, as it always does, demonstrating that small forces, when given time, can leave a planetary imprint without ever taking control. Carbon never truly vanishes from Earth. It shifts position, moving between air, water, rock, and life, carried along pathways shaped by physics and chemistry. What changes is not its existence, but where it resides and how long it remains there. Most carbon cycles quickly. It passes from atmosphere to ocean, from ocean to life, and back again through respiration, decay, and exchange. These movements occur over years, decades, sometimes centuries. They create balance through motion, ensuring that no single reservoir holds too much for too long. Burial is different. When carbon becomes locked into sediment, it leaves the active cycle behind. Exchange slows dramatically. What once moved freely now settles into stillness, isolated from the atmosphere by layers of material and time. This removal does not erase carbon, but it changes its influence. Because burial operates slowly, it rarely draws attention. The process unfolds grain by grain, layer by layer, without visible consequence on short timescales. Yet over thousands of years, its effects accumulate. Carbon stored below is carbon unavailable above, and the atmosphere responds to that absence. The Azolla Event highlights this distinction clearly. Carbon was not destroyed or transformed into something else. It was relocated. Through biological uptake and subsequent burial, a portion of atmospheric carbon shifted into long-term storage. The system did not lose carbon, it redistributed it. This redistribution mattered because climate responds to availability, not totals. Atmospheric carbon influences how much heat Earth retains. When carbon moves out of that space and into sediment, the climate system adjusts, even though the planet's overall carbon budget remains unchanged. Natural regulation operates on these long horizons. Weathering draws carbon slowly into rock. Sedimentation locks organic material away over immense spans. Volcanism returns some carbon to the atmosphere, but often on different schedules and in different places. Balance emerges not through symmetry, but through timing. This timing explains why natural climate shifts feel gentle when viewed from within them. Regulation depends on patience. Systems rarely correct imbalance quickly unless forced. Instead, they rely on persistent processes that work quietly until change becomes measurable. The carbon cycle, then, is less a loop than a circulation with pauses. Some pathways move rapidly, others delay movement for millions of years. Burial is one of the longest pauses available, and its role is therefore outsized despite its subtlety. Understanding this changes how planetary change is perceived. Dramatic events capture attention because they act quickly. Slow processes shape outcomes because they act continuously. The Azolla-driven shift demonstrates how carbon burial, sustained without interruption, can redirect climate without spectacle. It also reveals limits. Once carbon is buried, returning it to circulation takes time and energy. The climate system cannot simply reverse course at will. Natural regulation corrects gradually, respecting the timescales of the processes involved. This long view reframes Earth's behavior. The planet is not optimized for speed. It responds through accumulation, storage, and release distributed unevenly across time. Carbon moves according to these rules, and climate follows. What the Azolla event ultimately reveals is not an anomaly, but a principle. Carbon cycles define climate over long durations, not through disappearance, but through placement. Natural regulation works, but it works slowly, guided by persistence rather than urgency. Time shapes how Earth responds to change. In the deep past, shifts in climate unfolded over spans so long that they blended into the background of life itself. Alteration arrived gradually, layered into the planet's rhythms, carried forward without demanding immediate reaction. Ancient climate change moved at a pace measured in tens or hundreds of thousands of years. Carbon shifted slowly between reservoirs. Temperatures adjusted incrementally. Ice expanded by persistence rather than advance. Each change was small enough to be absorbed, then built upon by the next. The system had room to respond through adjustment rather than stress. Because the rate was slow, feedbacks unfolded gently. Oceans redistributed heat without disruption. Atmospheres altered circulation gradually. Ecosystems tracked shifting conditions over generations, reorganizing step by step. Change became something the planet incorporated, not something it resisted. Modern change operates on a different clock. Processes that once required vast stretches of time are now compressed into decades or centuries. Carbon enters and leaves systems far more quickly. Temperatures rise faster than many stabilizing mechanisms can respond. The same physical rules still apply, but they are being tested at unfamiliar speeds. Speed alters outcome even when causes appear similar. A slow increase allows buffering. A rapid one overwhelms those buffers. Feedbacks that once stabilized can become delayed, arriving after thresholds have already been crossed. The planet still responds, but response follows disturbance rather than accompanying it. This difference explains why ancient transitions often show continuity, while rapid changes create strain. Systems are shaped not only by what changes, but by how quickly it does. Rate determines whether adaptation is possible, or whether adjustment lags behind conditions. In the Azolla-driven cooling, change remained patient. Carbon removal accumulated quietly. Cooling followed gradually. Ice persisted without surge. The planet had time to redistribute energy and matter as conditions shifted. Nothing was forced to react suddenly. Modern change compresses influence into shorter intervals. Energy imbalances build before circulation can adjust fully. Biological systems experience altered conditions faster than they can reorganize. The planet is still capable of response, but that response arrives under pressure. This contrast does not imply fragility alone. It highlights sensitivity. Earth responds differently to the same mechanisms depending on tempo. Slow pressure reshapes equilibrium. Rapid pressure tests limits. Cause and rate work together. Carbon burial over thousands of years can cool a planet gently. Carbon release over decades can destabilize systems before balance reasserts itself. The material involved may be the same. The outcome is not. Understanding this difference reframes how change is evaluated. It is not enough to ask what drives a shift. It matters how quickly that driver acts. Speed determines whether feedbacks stabilize or amplify disturbance. Earth has always changed. Its history is written in transition after transition. What distinguishes the present from many ancient shifts is not direction alone, but pace. The Azolla Event shows what slow influence can do. Modern change reveals what happens when influence accelerates. Rate matters because time is the medium through which regulation operates. When change respects that medium, Earth adjusts smoothly. When it bypasses it, response becomes strained. The lesson carried forward from deep time is quiet but clear. How fast a planet is pushed shapes how it moves, just as much as why. Geography does not act loudly, yet it sets boundaries that determine what can and cannot unfold. In this case, location defined possibility long before any biological process took hold. The Arctic of this era occupied a rare position, shaped by land and sea in a way that constrained movement rather than encouraging it. The basin was not fully open to the global ocean. Its connections were limited, narrowed by continental arrangements that restricted exchange. Water could enter and leave, but not freely enough to erase local conditions. This partial enclosure mattered because it reduced the constant mixing that dominates most oceans. The Arctic became a place where change could linger. In open oceans, circulation disperses heat, nutrients, and organisms across vast distances. Currents prevent long-term isolation. Growth appears, peaks, and is diluted. Even productive blooms remain temporary because movement redistributes what accumulates. Dominance cannot hold when the system insists on balance through motion. The Arctic basin did not behave that way. Its enclosure slowed circulation and encouraged layering. Fresh water could gather at the surface without being immediately mixed away. Chemical differences could persist. Calm conditions could stabilize. Geography allowed the surface to retain its character instead of surrendering it to the broader ocean. This containment created an arena where small advantages compounded. Stability favored persistence. Persistence favored accumulation. Accumulation favored influence. None of these steps required intensity. They required location that limited correction. Geography also shaped light. Positioned at high latitudes, the basin experienced extended periods of continuous summer daylight. That illumination aligned with calm surface waters to support sustained productivity. Elsewhere, similar light conditions would still be disrupted by circulation. Here, geography allowed light to act without interruption. The placement of surrounding continents amplified these effects. Large landmasses delivered fresh water steadily, reinforcing stratification. The basin received input faster than it could release it. Over time, this imbalance became a defining feature rather than a temporary condition. If the Arctic had been fully open, this sequence would not have occurred. Stronger currents would have redistributed fresh water and nutrients. Surface isolation would have collapsed. Growth would have remained seasonal and limited. Burial would have diminished. Carbon removal would have lacked persistence. Climate influence would have softened into noise. Instead, geography held conditions in place long enough for biology to matter. The basin acted as a container, not sealed, but restrictive enough to favor continuity over dispersion. That restraint transformed ordinary processes into drivers of long-term change. This relationship between land, sea, and climate is consistent across Earth's history. Geography guides how systems respond by shaping pathways of movement and exchange. Mountains redirect winds. Continents steer currents. Basins trap water and material. Climate follows these contours. In this case, location shaped outcome not by force, but by permission. It allowed persistence where motion would have erased it. The Arctic basin did not cause cooling on its own. It made cooling possible by providing a space where influence could accumulate. Geography rarely creates change directly. It defines the conditions under which change can endure. Here, it guided climate behavior by limiting escape routes, proving that where something happens can matter as much as what happens. The world that allowed this sequence to unfold no longer exists. Its defining features were temporary, shaped by a specific arrangement of land, sea, and circulation that has since changed beyond return. What happened depended on isolation that the modern ocean no longer permits. Today's oceans are fully connected. Water moves between basins through wide, deep pathways that encourage constant exchange. Currents link hemispheres, redistribute heat, and mix surface and depth far more efficiently than in the past. This connectivity prevents the kind of long-lived separation that once defined the Arctic surface. Surface isolation, which proved essential, has largely disappeared. Fresh water entering the ocean is now rapidly dispersed, diluted by circulation that resists long-term layering. Stable caps cannot persist for thousands of years when mixing remains active. Calm gives way to motion before accumulation can take hold. This shift alone changes everything. Without sustained isolation, no single surface environment can remain chemically or physically distinct long enough to dominate. Productivity rises and falls, but it resets. Growth is checked by dispersal. Burial becomes limited. Carbon cycles back instead of remaining locked away. Geography has also moved on. Continental positions have changed. Gateways between oceans have opened fully. The Arctic no longer functions as a partially enclosed basin with restricted exchange. It has become part of a global system that values circulation over containment. Light conditions still vary by latitude, but they no longer align with the same stability at the surface. Seasonal rhythms remain, yet they unfold within an environment shaped by mixing rather than stillness. Extended daylight alone is not enough when persistence is absent. Modern biology reflects these constraints. Even organisms capable of rapid growth encounter limits set by turbulence, nutrient redistribution, and ecological competition. Dominance cannot extend uninterrupted across vast regions when the environment refuses to remain still. The carbon cycle also behaves differently. While burial continues in many settings, it does so in balance with return pathways that operate on shorter timescales. Long-term removal still occurs, but not through a single surface-driven mechanism acting without interruption. The system has diversified its regulation. These changes do not imply safety or permanence, they simply define difference. The pathways available to influence climate have shifted. What was once possible through quiet accumulation under rare conditions is no longer accessible. The Azolla Event belonged to a narrow window in Earth's history. It required partial enclosure, prolonged calm, sustained isolation, and uninterrupted repetition. Remove any one of these elements, and influence softens before it can shape the whole. Modern oceans lack that combination. Their strength lies in connection. Their defining trait is movement. These qualities resist the kind of long-term surface dominance that once allowed biology to leave such a deep imprint. This does not make Earth static. Change continues, guided by different mechanisms operating within today's structure. The planet remains responsive, but the routes available for transformation evolve alongside its geography. The event cannot repeat itself because the stage has been dismantled. The actors may still exist, but the setting no longer allows the same performance. What once unfolded through isolation now encounters connection at every turn, ensuring that this particular chapter remains confined to the past, a product of conditions that no longer align. Nothing changed all at once. No single season carried weight on its own. The planet did not respond to any individual moment because none of them were large enough to matter in isolation. What shaped the outcome was repetition, layered so gently that it blended into the passing of time. Growth occurred again and again, following the same quiet rhythm. Plant matter accumulated at the surface, spread, and eventually disappeared from view. Each cycle looked ordinary on its own, indistinguishable from countless others that came before and after. Yet the planet remembered all of them together. Death followed growth without drama. Organic material sank and settled, slipping below the reach of currents and oxygen. Burial followed death, not as an event, but as a process that never stopped. Fine particles stacked patiently, sealing carbon away a fraction at a time. No layer announced itself as important. Importance emerged from persistence. Time acted as the final ingredient. With enough of it, even subtle processes gained influence. Carbon moved slowly from one system into another and then remained there. The atmosphere adjusted not because it was forced, but because inputs changed steadily without reversal. Earth responded because pressure never relented. This pattern appears repeatedly across the planet's history. Mountains rise not through single uplifts, but through countless small movements. Valleys deepen through grains, carried away year after year. Continents reshape coastlines through accumulation rather than collapse. Earth rarely changes through singular moments. It changes through continuity. What makes accumulation powerful is that it resists erasure. Short disturbances fade, persistent ones shape baseline conditions. Growth that returns every year matters less than growth that never fully resets. Burial that occurs intermittently leaves little trace. Burial that continues uninterrupted reshapes systems. The Azolla Event followed this rule precisely. Growth alone would not have altered climate. Burial alone would not have mattered without repetition. Time alone does nothing without process to carry forward. Together, they formed a sequence that Earth could not ignore. This way of changing favors patience over force. It allows systems to adapt while still guiding them somewhere new. Nothing needed to break for the planet to move. Balance shifted because inputs changed, not because structure failed. Accumulation also explains why results can feel sudden when viewed in hindsight. Once thresholds are crossed, outcomes appear clear. Ice persists, climate settles. Yet the work that made those outcomes possible unfolded quietly, hidden behind familiarity. By the time change becomes visible, it has already been underway for ages. This is why Earth's history often reads as calm, punctuated by transitions that seem to arrive without warning. The warning was always present, spread thinly across time. Accumulation does not call attention to itself. It waits. The lesson carried by this event extends far beyond a single plant or era. It shows that influence does not require intensity. Given enough repetition, small processes shape planetary behavior. Growth leads to death. Death leads to burial. Burial alters cycles. Time turns movement into direction. This is how Earth often changes. Not through moments, but through momentum built patiently, one cycle at a time, until the path forward quietly diverges and never fully returns. The importance of this story does not fade with age. Its relevance persists because it reshaped the long arc of Earth's climate, setting conditions that still define the planet today. The cold poles, the presence of enduring ice, and the structure of modern circulation all trace part of their lineage to this quiet turning point. Long-term climate states are not fleeting moods. Once established, they guide patterns for millions of years. The cooling that followed the Azolla event did not simply pass. It settled into Earth's baseline, altering how heat moved, how oceans behaved, and where ice could survive. The planet did not return to its earlier warmth because the systems that supported that warmth had changed. Polar ice stands as the most visible legacy. Its persistence is not an inevitable outcome of latitude alone. Ice requires conditions that allow survival through seasonal cycles. The transition that enabled this persistence unfolded gradually, but once achieved, it reshaped Earth's identity. A world capable of sustaining polar ice behaves differently from one that cannot. This story also reveals climate sensitivity. Small, sustained changes in carbon availability produced consequences that extended far beyond their point of origin. The relationship between carbon and temperature is not abstract. It operates continuously, responding faithfully to cumulative influence. Even modest shifts matter when they endure. Sensitivity does not imply fragility, it reflects responsiveness. Earth reacts because its systems are interconnected. When one component changes slowly and persistently, others adjust. The Azolla event shows that climate responds not only to dramatic forces, but to steady pressure applied over time. Equally important is what the story reveals about patience. Change did not arrive through upheaval, it arrived through waiting. Processes unfolded at their natural pace, and the planet responded in kind. Regulation worked because it was given time to operate. Feedback stabilized because they were not overwhelmed. This patience contrasts sharply with how change is often imagined. Climate history is frequently framed around catastrophe, yet much of Earth's transformation occurs through accumulation. The most influential shifts can be the least conspicuous while they are happening. The story still matters because it broadens understanding of how Earth works. It demonstrates that life and environment are not separate actors. They influence one another continuously, sometimes in subtle ways that only become clear long after the fact. It also grounds abstract concepts in reality. Carbon cycling, climate feedbacks, and system balance are not theoretical. They have shaped the planet in tangible ways. Polar ice exists in part because carbon moved and stayed moved. There is no urgency embedded in this story, only perspective. It reminds that Earth's changes often unfold beyond human timescales, governed by persistence rather than immediacy. Influence accumulates quietly until it becomes structural. The Azolla Event matters because it left a lasting imprint without spectacle. It explains why Earth looks the way it does now. It shows that climate is sensitive, yet patient, responsive, yet deliberate. In understanding this chapter, the present world becomes less accidental. The cold at the poles, the shape of circulation, and the endurance of ice are not isolated features. They are consequences carried forward from a moment when something small, repeated endlessly, helped guide the planet into a new long-term state that still surrounds us today. Balance on Earth is never fixed. It shifts continuously, guided by interactions that operate without oversight or intent. When conditions drift, responses emerge from within the system itself. Chemistry reacts. Life adapts. Together, they guide the planet back toward workable states. Imbalance begins quietly. Carbon accumulates or diminishes. Temperatures trend upward or downward. Ocean chemistry shifts slightly from familiar norms. None of these changes demand immediate correction. Earth does not react to every deviation. It absorbs variation until thresholds encourage response. Chemical processes form the first layer of adjustment. Oceans exchange gases with the atmosphere, moderating concentrations over time. Minerals, weather, binding carbon into rock. Temperature alters solubility, shifting how much carbon water can hold. These reactions follow physical laws, responding automatically as conditions change. Life adds another dimension. Organisms interact with their environment constantly, drawing energy, releasing waste, building structure. Through growth and decay, life moves elements between systems. It accelerates some pathways and slows others, not with purpose, but as a consequence of metabolism and survival. Sometimes these two domains act independently. At other times, they intersect. Biological activity alters chemistry. Chemical conditions shape biological opportunity. Feedback emerges from their overlap rather than from either acting alone. The system adjusts through interaction. The Azolla Event illustrates this integration. Chemistry allowed carbon to influence temperature. Geography created conditions for isolation. Life responded by growing vigorously. Chemistry followed by locking carbon into sediment. Life receded. The system shifted because multiple processes aligned, each reinforcing the others without central control. Self-adjustment does not imply optimization. Earth does not seek ideal states. It settles into configurations that satisfy constraints imposed by energy balance, material availability, and structure. When those constraints change, the configuration shifts accordingly. These adjustments rarely appear dramatic in real time. They unfold at speeds dictated by the slowest processes involved. Chemistry moves faster than tectonics, slower than weather. Biology operates across overlapping timescales. The combined response reflects this complexity. Feedbacks stabilize outcomes once new states emerge. Ice reflects light, reinforcing cooler temperatures. Cooler oceans absorb more gas, altering atmospheric composition. Change circulation redistributes heat differently. Each response becomes part of the background that shapes future behavior. This self adjustment explains continuity. Earth carries memory in its systems. Sediments preserve past conditions. Ice records atmospheric composition. Living lineages adapt to new baselines. Change does not erase what came before, it builds upon it. The planet has adjusted many times without external force. Warm periods gave way to cooler ones. Ice advanced and retreated. Oceans opened and closed. In each case, response came from within, guided by the interaction of chemistry and life across time. Understanding Earth as a self adjusting system reframes change itself. Shifts are not interruptions, they are outcomes of ongoing processes responding to imbalance. The system is neither fragile nor rigid, it is responsive. This responsiveness carries no urgency and no reassurance. It simply describes behavior. Earth responds because it must, following the pathways available at the time. Sometimes chemistry leads. Sometimes life amplifies the change. Often, both work together. The story of Azolla fits within this broader pattern. It is not an exception, it is an example. Earth adjusted because conditions shifted and the tools for response were already present. Through chemistry, through life, through their quiet collaboration, the planet moved into a new state and carried that adjustment forward. There was no observer standing on a shoreline when this transition unfolded. No memory carried it forward through story or record. The world changed long before perception could accompany it, shaped by forces that did not require witnesses to proceed. Human history occupies only a thin layer at the surface of time. The transformation described here moved beneath that layer entirely, operating at depths inaccessible to experience. Ice advanced, carbon settled. Circulation shifted. All of it occurred without eyes, to follow the motion or language to describe it. Yet this absence of witnesses does not make the change distant. It makes it foundational. The conditions that define the modern planet were shaped during that unseen interval. Every cold current, every persistent ice sheet, every climatic boundary carries a trace of that earlier adjustment. The poles are the most visible inheritance. Their cold is not merely a product of latitude, it reflects a planetary state that permits ice to endure across seasons and centuries. That endurance was earned through gradual shifts that unfolded long before humans arrived to name them. Living within this outcome means inhabiting consequences without memory of cause. The planet feels stable because the transition is complete. The adjustment has settled into background. What once required immense spans of time to establish now appears permanent, even though permanence is only a temporary agreement between systems. The past remains active because Earth stores change rather than discarding it. Carbon buried millions of years ago still shapes atmospheric composition today. Ice that learned to persist continues to influence circulation and reflection. Ancient adjustments define modern behavior. This continuity blurs the boundary between past and present. The world does not reset when new species arrive. It carries forward every change that altered its balance. Humans entered a planet already shaped by countless unseen processes, inheriting climates whose origins lie far outside lived experience. Understanding this reshapes perspective. The present moment is not isolated. It is embedded within a much longer story, one that continues to operate quietly beneath daily variation. Every cold wind from the poles traces its ancestry to conditions set long ago. This does not imply nostalgia or loss. It simply describes layering. Earth adds new chapters without erasing earlier ones. The Azolla Event did not end when the plant receded. Its influence persisted, woven into circulation, temperature, and ice. The idea that the past remains active challenges simple timelines. What happened millions of years ago did not stop happening. It transitioned into structure. The effects moved from process into condition. Human life now unfolds within that condition. The climate experienced today is not only the result of recent influences, it is also the outcome of deep time adjustments that continue to express themselves through the planet's systems. A world no human ever saw still shapes every human experience. The cold poles stand as quiet markers of that truth. They remind that Earth changes without announcement, without witnesses, and without regard for who may arrive later. The past is not gone, it is present, operating steadily beneath familiar patterns. The planet remembers what life does, even when no one is there to watch. Understanding this event has never depended on a single discovery. It has emerged gradually, assembled from fragments of evidence that continue to grow clearer with time. Even now, the story is not closed. It remains a subject of refinement rather than revision. One focus of ongoing work is the exact rate at which carbon was removed from the atmosphere. Sediment layers preserve the result of that removal, but translating thickness and composition into precise quantities requires careful interpretation. Small differences in burial rate calculations can alter estimates of how quickly atmospheric carbon declined. The overall trend is clear, yet its exact slope continues to be resolved. Closely tied to this is the duration of biological dominance at the surface. Evidence indicates persistence across long spans, but defining precise boundaries remains challenging. Sediments record presence and absence unevenly, influenced by local conditions and later disturbance. Determining how long Azolla maintained near continuous coverage across large regions depends on increasingly fine resolution data. Ocean circulation during this period is another area of refinement. Models suggest restricted exchange, yet the degree of that restriction likely varied over time. Gateways may have opened and narrowed intermittently. Freshwater input fluctuated with climate and geography. Understanding how these changes influenced stratification remains an active pursuit. These circulation details matter because they shape interpretation of cause and effect. The balance between isolation and mixing determines how stable surface conditions truly were. Slight adjustments to circulation models can influence estimates of productivity, burial efficiency, and feedback strength. Isotopic analysis continues to sharpen the picture. Advances in measurement allow scientists to distinguish between carbon sources with greater precision. Subtle shifts in isotopic ratios reveal how plant material moved through the system and where it ultimately settled. Each improvement refines timing and scale without overturning the broader narrative. Drilling technology has also evolved. New cores extend records deeper and wider across the Arctic basin. These samples fill gaps left by earlier expeditions, linking isolated observations into a more continuous story. With each addition, uncertainty narrows. What has not changed is the structure of the event itself. The sequence remains stable. Biology contributed sustained carbon removal. Geography allowed persistence. Climate responded gradually. Refinement adds clarity, not contradiction. Science advances in this way. It does not replace understanding wholesale. It sharpens edges, tightens constraints, and improves resolution. The picture becomes clearer without changing its subject. Uncertainty here is not weakness. It reflects complexity. Earth systems rarely leave behind clean records. They preserve signals filtered through time, altered by later processes, and incomplete by nature. Working within that complexity is part of reconstruction. Each refinement deepens confidence. The more detail emerges, the more consistent the story becomes across independent lines of evidence. Chemistry, sedimentology, biology, and modeling continue to converge. This ongoing work highlights another truth about Earth history. Understanding is never final. It evolves as tools improve and questions become more precise. The Azolla Event remains a clear example of quiet planetary change, even as its finer details continue to sharpen. The broad shape is already visible. Carbon moved, climate shifted, ice persisted. What science refines now are the contours, bringing the image into sharper focus without altering its form. The Earth does not forget. It stores its history quietly, pressed into layers that accumulate without intention or pause. Rock forms grain by grain, ice builds season by season, sediment settles particle by particle. Together, they become a record that does not rely on memory, only on persistence. Every change leaves an imprint somewhere. Some are dramatic and easy to recognize, marked by disruption and contrast. Others arrive so gently that they blend into continuity. These quieter events are often the most enduring, precisely because nothing interrupts them. Sediment preserves this patience especially well. Each layer seals what came before, protecting signals from erosion by time. Organic material becomes carbon-rich strata. Chemical shifts alter isotopic signatures. What was once part of moving systems becomes still, locked away where later processes can read it. Ice records differently. It traps atmosphere itself, preserving composition as bubbles frozen in place. Layer upon layer forms a timeline of conditions, revealing slow trends rather than sudden breaks. Ice remembers temperature not through drama, but through accumulation. Rock carries memory over the longest spans. Carbon buried deeply becomes limestone. Pressure and heat transform sediments into stone. What began as life or water becomes structure, enduring long after the processes that shaped it have ended. These records show that silence does not mean absence. Change does not require noise to matter. The Azolla Event left no crater and no ash. Its signature appears instead in thickness, composition, and chemistry spread across immense distances. Quiet processes wrote the story slowly, and the Earth kept it. The planet carries forward these marks even when the cause disappears. Azolla receded, conditions shifted, surface dominance ended, yet carbon remained buried. Ice learned to persist. Circulation adjusted and stabilized. The memory of the event became part of the planet's framework. This long memory explains why Earth's present state reflects more than recent history. Modern climates are built atop ancient decisions encoded in stone and ice. The planet operates with context, responding to current forces through structures shaped long ago. Some of the most powerful forces act slowly because slowness allows permanence. Rapid events can alter landscapes, but slow ones redefine baselines. They change what is normal rather than what is visible. Once that change is set, it endures. The Earth does not distinguish between intention and accident. It records outcomes. If a process persists long enough to leave a mark, that mark becomes part of the system's starting point moving forward. Every new chapter is written on pages already filled. This continuity gives Earth its depth. Nothing begins from nothing. Each adjustment rests on prior ones, layered like sediment. The past remains active, not as repetition, but as structure that guides future response. The Azolla Event illustrates this truth clearly. A small plant influenced the planet, then vanished from prominence. The influence remained. Ice persists. Climate holds. The memory lives on without the presence of its source. This is how Earth carries time, quietly, faithfully, through rock, ice, and sediment. It holds on to change long after the motion has stopped. Some forces fade quickly. Others settle into the planet's bones, shaping everything that comes after. The long memory of the Earth ensures that even the gentlest moments, given enough time, can echo across millions of years, guiding the present from deep within the past.